Hello, and welcome to the Complete History of Science podcast. Modern science has had a transformative impact on the modern world. When we think of science, one of the first things that comes to mind are the technological innovations which have improved our lives. And if we're called to defend science, we often fall back on these technological advancements to argue that science is both practically useful and does indeed actually work. However, the other consequences of scientific advancement have been more subtle. Science has not only changed our lives materially, but it's also changed our perceptions of the world we live in, and this is especially true in the case of astronomy. In the ancient world, most people conceived of the universe as having a very limited extent, with the Earth at the centre and the celestial bodies orbiting relatively close to the Earth. Since then, however, almost every advance in astronomy has seen our perception of the size of the universe expand, and by extension, our own place within it shrink. We can see this in two ways. There's a metaphorical shrinking, where we see ourselves as less important and central because of the enormity of the universe. But there's also a literal meaning, because every scientific advancement in astronomy has also been accompanied by better and more accurate measurements of the distances involved. Measurement and quantification have been very important in the development of science. By measuring things, either the very large or very small, we make them tangible to our human senses. It's no coincidence that many of the earliest units for distance were based on the proportions of the human body. For example, the hand was a unit literally based on the proportion of an adult male hand. Similarly, measurements were based on human experience. For example, a league was thought to be the distance a person could reasonably walk in an hour. As astronomy has progressed and our understanding of the world has changed, we've created units which are further and further beyond our experience. For example, the light year and the parsec measure distances which are unimaginably large and demonstrate how much our own place in the universe has shrunk compared to the vastness of space. However, quantification and measurement aren't necessarily universal desires. As we discussed in the last episode, the very early Greeks weren't especially interested in measurement, content to make qualitative observations or mathematical models, which didn't necessarily align with the real world. Nevertheless, an important leap for Greek science in the ancient world was made when the Greeks began to make measurements. And two of the most important figures in this change was Eratosthenes and Aristarchus. Eratosthenes was an Alexandrian Greek living in the 3rd century BC. He was the chief librarian of the Great Library of Alexandria, and a man of wide learning, being a mathematician, geographer, historian, poet, as well as early astronomer. One of Eratosthenes' main challenges was that he was keen to measure the circumference of the Earth. You see, the ancient Greeks had known the Earth was a sphere since at least the 5th century BC, and they had many arguments for this. One of the simplest was, if you watch a ship sail over the horizon, its sail could be seen before its hull comes into view, implying a curvature to sea level. The ancient Greeks also put into their use their knowledge of astronomy to derive sophisticated arguments for the shape of the Earth. For instance, multiple Greek writers point out that the visibility of the constellations changes depending on the location where they're viewed. Canopus, for example, one of the brightest stars in the night sky, was visible from Egypt, but not from more northerly Greece, implying at least some curvature from north to south. Aristotle was important for propagating these ideas of a spherical Earth throughout the Greek world, and had his own arguments for this based on the observations of the lunar eclipse. He noticed that during a lunar eclipse, the Earth casts a curved shadow upon the Moon, providing fairly unambiguous evidence for the Earth's shape. Despite the overwhelming evidence for the shape of the Earth, the task of measuring the size of the Earth seemed hopelessly impractical at the time. This seems even more so when you consider that the desert of the Sahara, as well as the Atlantic Ocean, which was unnavigable to ships at the time, provided hard limits for how far any individual could travel. The ancient Greeks were aware of other places and other cultures, but their primary experience was confined to the people around the Mediterranean. However, the ancient Greeks were undoubtedly resourceful, and Eratosthenes made his measurements of the Earth using the simplest of scientific devices, the gnomon. This remarkably versatile tool was discussed in a previous episode, where it was used to accurately calculate the solstice and the equinoxes. The Greeks may have learned of the gnomon from the Babylonians, who in turn may have learned about it from the Egyptians. However, it's such a simple device, it could have been invented and reinvented repeatedly across time and space, because a gnomon is just a vertical stick set in the sun. You use it to measure the length and direction of the shadow cast by the sun as it passes across the sky. For example, the shortest shadow appears at noon on the summer solstice, when the sun is at its highest point in the sky. Eratosthenes' measurement was based on this, but also the fact that the length of the shadow cast depends on latitude. Latitude is a measure of how far north you are, which changes the angle at which the sun's rays strike the Earth. This means that two measurements made with a gnomon at the same time at different latitudes will be a different length. Specifically, Eratosthenes knew that on the summer solstice, the shadow cast at noon in Alexandria will be at its shortest extent, but will still be finite and measurable. However, at the same time, further south in Syene, which is modern-day Aswan in South Egypt, the shadow cast by the sun will be close to nothing, as the sun is directly overhead. This is because of Syene's latitude, close to the Tropic of Cancer. Eratosthenes could have left his observations there, and simply taken it as another piece of evidence for the sphericity of Earth. However, he realised that these observations could instead be used to calculate the circumference of the Earth. To understand this, it's helpful to imagine a line stretching directly upwards from the ground, which we call the zenith. A gnomon, properly set up, should point directly upwards towards the zenith. At most times and in most places, the sun is not directly above us, hence there is some finite angle between the zenith and the sun's rays, which cause the shadow. By measuring the length of the shadow using the gnomon, the angle between the zenith and the sun's rays can be measured. However, at noon on the summer solstice at Syene, the sun is directly overhead, implying that the angle between the two is 0. Now at this point you may be asking yourself, so what? Well, Eratosthenes' realisation was that on the summer solstice, the difference in the angle between the zeniths and the sun's rays would correspond to the difference in latitude between Alexandria and Syene. When Eratosthenes took his measurements at noon on the summer solstice in Alexandria, he calculated that the angle between the sun's rays and the zenith was 1/50th of a circle. This implied that the distance between Alexandria and Syene was also equivalent to 1/50th of a circle. Eratosthenes then had someone measure the distance between Alexandria and Syene, which was measured at 5,000 stads, implying that the circumference of the Earth was 50 times 5,000, or 250,000 stad. Unfortunately, it's difficult to say with any precision quite what this equates to in modern units of distance, as their unit, the stad, varied in length between 100 and 210 metres. However, taking this range of estimates for the stad, it would certainly be within the right ballpark, corresponding to a measurement 10 to 30% from the modern accepted value of 40,000 kilometres. This was a remarkable achievement in itself, and Eratosthenes' methods also formed the basis for the measurement of latitude, a key component of navigation. From this point, measurement began to be seen as a key component in the practice of astronomy. But while Eratosthenes' work was remarkable, he was followed by another early astronomer who attempted an even more ambitious measurement. Aristarchus was a Greek, born around the beginning of the 3rd century BC on the island of Samos near Turkey. As with many other figures in early astronomy, very little detail of Aristarchus' life is known. Indeed, very little of his work has survived, and only a single original work of his has been reproduced. However, references to his work exist in the work of other writers, most notably Archimedes. We mentioned Aristarchus in the last episode because his most famous contribution to the history of science is that he's the first person to unambiguously suggest the heliocentric model. As we have discussed, virtually all Greek astronomy followed the general outline set down by Aristotle and Eudoxus. That is, there are two spheres, the celestial, containing all of the celestial bodies such as the sun, moon and stars, and the earthly, containing, well, the earth. The general picture was that the heavenly celestials revolved around the earth, producing day and night, the seasons and so forth, the so-called geocentric model. However, in his book The Sand Reckoner, Archimedes makes reference to a theory of Aristarchus. To quote, Aristarchus of Samos brought out a book consisting of some hypotheses, in which the premises led to the result that the cosmos is many times greater than now so called. His hypotheses are that the fixed stars and the sun remain unmoved, that the earth revolves about the sun in the circumference of a circle, the sun lying in the middle of the orbit, and the sphere of the fixed stars, situated about the same centre as the sun, is so great that the circle in which he supposes the earth to revolve bears such a proportion to the distance of the fixed stars as the centre of the sphere bears to its surface. Here, Aristarchus is the first person to seriously consider that the geocentric model may be wrong, and in fact, the earth revolves around the sun. Not only that, but Aristarchus considers the implications of this model, correctly realising that it implied a universe that was many times bigger than the Greeks had imagined. It's difficult to appreciate today, but the Greeks imagined that the so-called fixed stars weren't much further away than the other celestial bodies, such as the moon and sun. Aristarchus, however, realised that if the earth was moving, then this would imply that the stars had to be much, much further away than previously thought. To understand this, imagine you're in a field with two trees at the centre. As you move around the trees, your perspective changes. That is, they seem to change position with respect to each other, due to the phenomenon known as parallax. Likewise, if the Earth really is moving and the stars are relatively close, we would expect parallax to cause the position of the stars to change with respect to one another. We absolutely do not observe this to any great extent on Earth. For example, the constellations remain relatively unchanged throughout the year. To resolve the apparent inconsistency with his idea, Aristarchus suggested that it implies the stars are very far away. Imagine again two trees, but this time on a distant hillside. Now as you move, the change in perspective is very slight, as the further away the objects are, the less parallax you'll observe. The conclusion which he reached was that if the Earth is moving and we don't observe the parallax of the stars, this implies the stars are very far away. It's astonishing that someone in the 3rd century BC not only suggested a heliocentric solar system, but also its implication of a vast universe. However, his idea was to have little influence and was largely ignored by later Greek astronomers. It wasn't until the 16th century that astronomers, who probably knew nothing of Aristarchus' suggestion, began to rediscover the idea of a heliocentric solar system and grapple with its implications. Indeed, even in Aristarchus' other work, he makes no mention of the heliocentric model. Instead, his surviving work attempts an extraordinarily ambitious measurement, which was to find the size and distances between the Earth, Sun and Moon. He starts by attempting to measure the ratio of the distance between the Sun and the Moon. To do this, he observes the Sun and Moon during the lunar quadrature, that is, when we have a quarter moon. Aristarchus estimated that this occurs when the angular distance between the Sun and the Moon is around 87 degrees. Aristarchus was working before trigonometry had been fully established in the Greek world, so instead uses geometrical constructions to give an upper and a lower limit. He manages to prove that the distance to the Sun is somewhere between 18 and 20 times that of the Moon. This would of course be much easier nowadays, and using trigonometry, we can find out the ratio is actually 19.1 using Aristarchus' estimate of 87 degrees. From Aristarchus' results, it's possible to reconstruct his measurements to gain an absolute distance in terms of the Earth's radius. This would correspond to 20 Earth radii for the distance to the Moon and some 380 for the distance to the Sun. Next up, Aristarchus tackles the relative sizes of the Sun and Moon. For this, he uses the fact that they each have a roughly similar angular diameter when measured from Earth. This is obvious when observing a solar eclipse, as the Moon almost perfectly covers the area of the Sun. Aristarchus sets up another geometrical construction, similar to when the Moon experiences a lunar eclipse. Again, he calculates that the Sun's diameter is roughly 18 to 20 times greater than the Moon. Putting this as an absolute measurement in terms of the Earth's size gives an estimate for the Sun of 6.67 Earth diameters and the Moon as 0.351 Earth diameters. As you may have noticed by now, Aristarchus' measurements weren't wholly accurate. Some of his conclusions were in the very general correct. He found that the Moon is smaller than the Earth, and the Sun is considerably larger. Similarly, he found that both the Moon and the Sun were some sizable distance away from the Earth. However, the actual values that he arrived at for these sizes and distances, especially of the Sun, are fairly large underestimates of the real values, and there are several reasons for this. Firstly, the values Aristarchus used in some of his calculations were not very accurate. For example, the estimate for the ratio of the distance of the Moon and Sun of around 18 to 20 times is a long way from the true value, where the Sun is actually 400 times further away than the Moon. However, it's unfair to blame Aristarchus for this. As mentioned, Aristarchus estimated that the angle between the Moon and the Sun at lunar quadrature was around 87 degrees. In reality, it's around 89 degrees and 51 arc minutes, only 9 arc minutes short of a right angle. Even at the height of Greek astronomy, such an accurate calculation wouldn't have been possible with the available equipment. Also consider, how, for example, do you calculate the exact moment the Moon is in quadrature? Or, how do you decide where the centres of the Sun and Moon are with any accuracy? The second reason is slightly more subtle. Aristarchus could have improved some of his other estimates fairly easily, for example, by taking a better measurement of the angular diameter of the Moon, a measurement that can be made fairly easily using just a ruler. The astronomer and historian James Evans has shown it would be possible to gain very good estimates of the size of the Sun and the Moon within 10% of the real values, if a more realistic value of 0.5 degrees were used for the angular diameter of the Moon, rather than the 2 degrees used by Aristarchus. Evans suggests that the reasons for this are that Aristarchus didn't actually take the measurement at all, but instead only estimated it. This seems likely if we remember the Greeks in Aristarchus' time weren't that interested in measurement. In this context, Aristarchus was more of a transitional figure, who, while interested in showing that measurement was possible, was not wholly invested in actually carrying through those estimates. Despite this failure to fully grapple with measurement as a science, Aristarchus had demonstrated to his successors that astronomy could be quantitative. Greek science after Aristarchus ceased to simply be a matter of philosophical arguments, but would start to become dependent on measurement and observation. This was a great leap in the history of science, and Aristarchus' work would have a lasting influence on the two great Greek scientists who followed, Hipparchus of Nicaea and Claudius Ptolemy. These two astronomers would improve upon Aristarchus' methods and would more fully accept the need to combine careful measurement into their mathematical models. So in the next episode, we'll move on to the figure I regard as the greatest astronomer of antiquity, Hipparchus of Nicaea.